we have seen a two equation model for turbulence in terms of two quantities K, the turbulent kinetic energy, and epsilon, the rate of dissipation of the turbulent kinetic energy, being used to evaluate the turbulent viscosity or the eddy viscosity associated with turbulent flows. It is very important in turbulence modeling to consider the near wall turbulence, because that is a very important region in terms of the production of turbulence and so on. So we have to treat the near wall turbulence properly so as to get a solution which is appropriate. So what we mean by near wall turbulence is that in our model we have written equations like dou k by dou t plus dou by dou x j of ujk, the mean is equal to dou x j of nu t by sigma k, dou k by dou x j representing the turbulent diffusivity of kinetic energy plus a production term and a rate of dissipation term, this is the epsilon, and pk here is the production term which is minus ui prime uj prime bar in terms like this. So where you have large mean velocity gradients, you have a production of turbulence which goes into this as a source term, and this itself is represented in terms of nu t dou u I bar by dou x j plus dou u j bar by dou x I, where nu t is given as c mu k square by epsilon. We have a similar transport equation for epsilon, and therefore we have two standard equations of the generic scalar transport equation representing k and epsilon, which go together to determine the turbulent viscosity, which goes on to determine the turbulent or Reynolds stresses in terms of mean velocity gradients and the turbulent viscosity. Now what about the boundary conditions? We know that any partial differential equation, any differential equation cannot do without the boundary conditions and initial conditions as appropriate. Since we are talking about mean quantities, k and epsilon here are mean time average quantities. So wherever you have standard boundary conditions like symmetry plane, plane of symmetry, and those kind of things are still applicable. So when you have a plane of symmetry like flow through a duct which is exactly identical with respect to the center plane, then we can calculate the flow field either in this part or in this part. It is not necessary to go through this, in which case along this plane one can say that if you say that this is x and this is y and this is y equal to 0 and y equal to minus h plus h, like that, one can say that dou k by dou y at y equal to 0 is 0, and similarly one can say that dou epsilon by dou y at y equal to 0 is equal to 0. So these kind of boundary conditions natural to the flow are quite valid, but what is important in many practical cases is also the boundary conditions at the wall, and that is where we have to make a special distinctive characteristic of turbulent flow. Ideally one would say that at the wall, in this case that is at y plus or minus h, at y equal to plus or minus h, we know that the velocities has to be 0. The velocity have to be 0 by the no slip condition in laminar flow. Even in turbulent flow this no slip condition is valid, but we cannot use this boundary condition with this kind of turbulence model, because this turbulence model assumes that the turbulence is fully developed and it is strong enough that most of the diffusion and the production terms, these are uninfluenced by the molecular properties. For example, we have said that ui uj prime, these Reynolds stresses, are functions only of nu t, which is a function only of k and epsilon. So this is purely a turbulent quantity, and therefore this model is appropriate only for high Reynolds numbers. So it is a high Reynolds number turbulence model. And so one would expect the Reynolds number of the flow to be of the order of 20,000 or 50,000 or greater for this flow to be valid. And also very close to the wall we have the special feature that turbulence is damped. We have seen typical plots of for example u RMS, that is u prime square bar. It would actually go something like this, and then it would come out like this, and this maximum is very close to the wall. It may be 0.01 of the non-dimensional length. So that is, let us say, the distance divided by characteristic length. It can be something like that. So within that you have a very steep variation of typical turbulence quantities, and even the other things will go like this, and towards the end they all may become, as you move away from the wall you may have isotropy, but very close to the wall we have severe non-isotropy. And in this model we are not considering the non-isotropy of the turbulence, because we have an isotropic eddy viscosity which is being brought in here, and it is a function of only the scalar quantities k and epsilon, and there is no possibility of introducing anisotropy that is very strong very close to the wall. As you move away from the wall then you have more of isotropy. So that is one reason why we cannot make use of this model very close to the wall. You also have significant damping of turbulence very close to the wall, and finally we have said that C mu is a constant, and we have said that is something like u prime v prime bar by u prime square v prime square bar square roots. Okay, so it is some non-dimensionalized variation of u prime v prime bar like this with a minus sign, and we have said that this quantity is mostly constant like this, and this has a value of 0.3 with respect to distance from the wall. Okay, so the distance from the wall increasing, this reaches a constant value. Based on this we have put a C mu value of 0.09. We have made this a constant, and it is not a function of distance from the wall, but very close to the wall this changes drastically, again like here. So that means that when you come very close to the wall the turbulent viscosity is no longer directly proportional to k and epsilon, but this constant functionality itself is a function of y, the distance from the wall. And also the k and epsilon, although they are 0 at the wall, they show very steep gradients close to the wall, okay, in the region very near the wall. So that means that if you want to resolve a very steep gradient going like this, you need to have very fine delta y here. Okay, so the delta y needs to be very small in order to resolve the very rapid variation of the turbulence quantities both k and epsilon in the region close to the wall, and that means that the number of grid points which are needed to discretize the given cross section will become very large. So there are a number of reasons. One is the non-constancy of the constants, the non-isotropy of the turbulent viscosity and the need for very small delta y. For all these reasons we cannot take this model very close to the wall. So we start calculating the variation of k and epsilon, for example the k as a function of x and y and epsilon as a function of x and y are calculated only from after a small distance from the wall. Within the small distance the turbulence quantities change very rapidly, but fortunately that change can be expressed in terms of local variables or what are known as inner variables. That means that the variation here, the variation of the mean velocity k and epsilon very close to the wall can be expressed in terms of dimensionless quantities y plus, which is defined as y u star divided by nu, where u star is the friction velocity and that is given as y wall shear stress divided by rho. It is square root of wall shear stress divided by rho divided by the kinematic viscosity of the fluid. Okay, so we are bringing in the kinematic viscosity of the fluid here, and we are non-dimensionalizing with respect to this friction velocity, which is a function of this. And now if you were to plot this mean velocity, which is again non-dimensionalized with respect to for example u max or u mean as in the average velocity in a pipe like that, then it shows a characteristic variation. It goes through like this and then becomes a fairly constant thing on a lawn plot where y plus is plotted like this, and within a distance of say over a distance of y plus of from 0 to 5 you have a linear variation between u plus and y plus. So this we call as u plus. So we know that 0 less than y plus less than 5, this u plus varies linearly with this, and between 5 and y plus of 30 or so, u plus is a fairly strong function of y plus. It is a nonlinear expression, and for y plus greater than 30, okay, and so we can put it like this 30 and up to well into the flow of the say of the order of say 100 or 200 or even 500 like that, depending on the flow and what sort of pressure gradient we have and all that. There is a region in which this u plus can be expressed as 1 by kappa ln y plus plus a constant b, where kappa is a constant. We are familiar, it is around 0.4, 0.38, 0.41, 0.42 like that. So this has a slope of about 2.5 when plotted as u plus versus ln y plus. So this is known as the logarithmic region. And this region here where your u plus is y plus is known as the viscous sublayer, and this is a buffer layer. So through this there is a more complicated variation here, but once you reach a distance of y plus greater than of around 30, you have almost a linear variation with log of y plus, and this is known to be valid. This logarithmic thing is valid for, it's a very universal velocity profile, this particular variation. It's universal because it's valid for flows with pressure gradient and with adverse pressure gradient and with favorable pressure gradient for boundary layer flows, for flows inside pipes, and for all these cases this is this sort of thing is valid up to a certain distance. So in this sense and this y plus of 30 is typically very small because the maximum y plus, for example, if you are looking at a flow between two plates and at a Reynolds number of the order of say 50,000, then if you say that this is 2h, then h plus, which corresponds to the maximum distance, is of the order of 5,000 or something like that. So this 30, which is the beginning of this logarithmic layer, is a small fraction of this whole thing, and we take advantage of this to say that we know the variation of the velocity parallel to the wall. Okay, so in this direction you have a velocity profile like this. We know this variation in the region very close to the wall, and it is related to the local shear stress in this particular way. So we put, if this is our overall domain, this is the center line here and this is the wall here. So we put a first grid point here, second point, third point like this. And instead of saying that u is equal to 0 at y equal to 0, which is the no slip boundary condition, we say that at this point, say u1 is given by 1 by kappa ln y1 plus b. So the boundary condition that we apply here, okay, this is u1 plus. So this u1 plus is the mean velocity at that point divided by the average velocity or the maximum velocity like that. So in that sense we specify the boundary condition in terms of we specify the value of the velocity at the first grid point, taking advantage of the fact that within this point here, where in such a way y1 plus is greater than 30. So we choose the delta y here. We choose the delta y here such that delta y plus is greater than 30, or let us say it is between 30 and 100 or 200 like this. So we choose a value which is not very close to the wall, but it is at a sufficiently long distance from the wall, such that it falls in the logarithmic region, because in the logarithmic region we have an expression, simple expression for u plus as a function of y plus. So if you know the distance, then using this we can get the non-dimensional velocity here. So this is the boundary condition that we use. So this is known as a wall function. Because close to the wall we are making use of an algebraic function u in terms of y here to represent the velocity, not from the it is not given by the momentum equation, nor is it given by the real boundary condition that at y equal to 0 u equal to 0. So we are saying that very close to the wall you have a velocity which is non-zero, and it is given by this universal velocity profile, and the velocity normal to the wall v is equal to 0 and w equal to 0 is the standard boundary condition that we give. What about k and epsilon? Even k and epsilon are given by similar functional values. One can show that k1, so that is the turbulent kinetic energy at the first point, provided the first point is between 30 and 100 in terms of y plus, is equal to u star square. where u star square is given in terms of this, and one can show something like this, and epsilon 1 at this point is given in terms of u star square by kappa y1, something where kappa is this 0.338 and y1 is the distance of the grid point from the wall. So in that sense we specify the values of u, v, w and k and epsilon at the first grid point, locating the first grid point at a sufficient distance from the wall such that the y1 plus lies between 30 and 100. The reason for this is that we do not want to get too close to the y, because then you have a steep variation and you have a slightly more complicated expression for this. And if you put too much, if you take your y plus maybe 200, 500 or 1000 into that, then this first grid point will be somewhere here, and in all this region you are not actually solving the momentum equation, you are making use of a known function. So in that sense we want to make sure that the region where we make use of, where we impose a functional variation is very thin compared to the overall flow domain. We would like to make use of as much of the flow domain to be computed by the momentum equations, and it is only very close to the wall where we have deficiencies with respect to the way that we are modeling turbulence here, we make use of the wall functions. So this approach enables us to use, for example, if you have a duct of a cross section like this, we can make use of a grid which is maybe 20 by 20 grid to represent the flow through this, or maybe 30 by 30. But if we do not have this wall function, and if we want to resolve this velocity profile all the way through this right up to this, then we have to make changes to this turbulence model. There are definitely those kind of turbulence models which enable us to calculate right down to y equal to 0, for which the boundary condition will be u equal to 0 at y equal to 0 and k equal to 0 and epsilon equal to 0. So you have the natural boundary conditions for such models, those turbulence models which make modifications to the standard high Reynolds number turbulence model in such a way that you take account of the anisotropy, that you take account of the damping of turbulence close to the wall and all that. So there are such kind of low Reynolds number turbulence models, and there are also models which like k omega type of model, where omega is related to epsilon by k. So instead of solving for k and epsilon like what we are solving here, we solve for k and omega and we get epsilon from this. So these kind of approaches are more amenable to go right down to the wall. So using those models we can resolve the full layer, but in such a case we can't use only this kind of grid, we may have to have delta y for these kind of models. Delta y close to the wall should be of the order of 1. So that means that if you have a flow such that the overall the maximum H plus is of the order of 5000, then your grid delta y here should start with 1 here, and then if you have uniform spacing you have 5000 grid points. So it should be 5000 by 5000. Okay, you probably do not need that, but over you would have in such a case a grid which is geometrically expanding. This is the center line, and here you will have a grid spacing which can geometrically which can increase in a geometric progression, but with the restriction that your delta y close to the wall is of the order of 1. and also from in order not to bring in numerical accuracies associated with a non-uniform grid, you would like delta y k divided by delta y k plus 1. So, that is this delta y divided by this delta y. Okay, so, that sort of thing, successive values to lie between 0.7 and roughly 1.4 is a general thumb rule, so as not to lose too much accuracy of discretization or approximation, finite difference approximations when we have this sort of expanding grid. So, because of this, you may not have to use 5000 by 5000, but definitely the number of grids to represent something like a square duct at a Reynolds number of 50,000 like this may increase up to 200 by 200, and that means it is a 100-fold increase in the number of grid points, and the computational time will also increase much more, maybe a factor of 100 square like that. So, that is why in the general case we try to use the wall functions in order to represent the turbulence variation very close to the wall. But there are special cases where we may want to go to these kind of models which enable us to compute the flow variables all the way to y equal to 0. Okay, for example, if you have a case of strongly accelerating flows, in such a case it is possible that the flow near the wall may become laminar. So, that is called relaminarization of turbulent flow. And one example is that, let us say that you have a wall here and then you have a protuberance like this. So, the flow is supposed to go through over this and then come out. There is a small hill associated with this, and in this you have an accelerating region and then you have a decelerating region. So, this acceleration of the flow, if it is strong enough, is supposed to damp out turbulence, and if the acceleration is sufficiently strong and sustained, the flow may become even laminar as it goes over the hill. And once it becomes laminar, your turbulent viscosity is 0. So, that means that your friction factor will be very different and the heat transfer coefficient will be different and all that. So, if you were to plot, for example, the Nusselt number, it may be something like this value here, but as you go over the hill it may come down and then it may go back like this. So, this drop in the heat transfer coefficient, the Nusselt number, is associated with the relaminarization of the flow, and if you want to capture those kind of effects, then you have to resolve the turbulence right up to the wall. So, in such a case you may have to use low Reynolds number version of these type of models, or the k omega type of models like this, to get these special effects. Otherwise we have this kind of fairly universal model, the k epsilon model, which can be used as a first to investigate, to calculate the turbulent flow without having to fix any constants. But even though this is considered as a fairly general model, there are modifications to this, for example, for strongly accelerating flows, for buoyant flows, and so in such cases people have come up with a different set of constants for this. And so if we know such information, if we have such information, then we can make use of those ad hoc fixes to the constants that go into the determination of k and epsilon as a function of x, y, z, and then the corresponding determination of the turbulent viscosity and so on. Now in that sense K-epsilon model can be considered as a good enough completely specified self consistent and a model which we can use straight away without having to give ad hoc fixes like we have to do for the case of mixing length model. But this has some deficiencies. One deficiency is the near wall treatment that we have seen, and that is that we have to make use of the wall functions, and that we cannot make use of the natural boundary conditions that at the wall we have k equal to 0 and epsilon equal to 0, but we have to fix, we have to assume a certain variation, or we have to impose certain variation close to the wall, some non-dimensional variation close to the wall in order to get a solution. Another problem with this is the assumption of isotropic viscosity here. The turbulent stresses here are proportional to the mean velocity gradients through an isotropic viscosity. Isotropic viscosity because this viscosity is independent of which of the 6 stresses that we are considering here, and this is isotropic because this is determined only by k and epsilon, which are again scalar quantities, which are therefore in that sense isotropic. So this isotropic viscosity is known to be not so good when you are considering for example a swirling flow where you have flow going like this, or with in a flow with a strong curvature you have flow going and then turning, so you have flow in a bend or flow in a coil tube, or flows with strong buoyancy. All these are cases in which the additional force field arising out of this special effect, the swirling nature and the buoyancy, these are directional, these are aligned only in certain components of the velocity. So you can say that these bring in source terms, additional terms only in certain momentum equations and not in other equations. So in such a case one can expect the different turbulent stresses to respond in different ways to the imposed external force field like buoyancy. So this assumption of isotropic viscosity it will give as a problem in such cases. And then this model is also unable to represent the different levels of u prime square, v prime square and w prime square at the wall, because one can, once we know nu t here and once we know these velocities, one can calculate the different stresses here, and for this kind of plane flow in which only du by dy is present, so that this is not present, we find that the turbulent stresses are considered to be the same, and one would say that u prime square is equal to v prime square is equal to w prime square is equal to two-thirds of k. Is the only thing that we can say about the level of this turbulence quantities, fluctuating components in each of the directions. So this equivalence of these things is implicit in this model, whereas experiments show that these can vary in different ways. And there are also experiments which show that this linear relation between the turbulent stress and the strain rate, in which we have made use of the for example the similar linear relation between the viscous stress and the strain rate in a fluid, this linearity assumption is also not correct. So there are certain experimental data which can be obtained or which can be explained only by a nonlinear variation between the turbulent stresses and the strain rates, and so we have also models, nonlinear two equation models and to represent the general anisotropy and the response of different turbulence stresses to an arbitrary force field, we have the so called Reynolds stress model. I am just writing in this box. In which a separate transport equation is solved for each of the 6 Reynolds stresses. In such a case, you have the 4 equations representing the time averaged contingent equation and the 3 time averaged momentum equations, and then there are 6 Reynolds stress components. So you have 6 additional transport equations for the 6 Reynolds stresses, and you still have an equation for epsilon, the dissipation rate, which appears in the Reynolds stress equations. So you have a total of 11 equations to be solved for a turbulent flow calculation, not just 4 as we do in laminar flow. In the case of K epsilon model, we have to solve 4 time average momentum equations and the contingent equation, and then 2 equations for K and epsilon. You have 6 equations. So by increasing the number of equations, one can bring in more and more sophistication into the calculation, and thereby we can be more accurate in our calculations, especially for certain cases where we have sufficient data to determine fully the constants that appear in the Reynolds stress equations. But there is also the side effect of trying to solve more and more turbulent equations, because the side effect is that the number of equations that we want to solve increases from 4 in laminar flow to 6 in the 2 equation model to 11 in the case of Reynolds stress model. This increases the computational time, and it also increases the coupling among all these equations. So therefore the convergence of these coupled equations is not it becomes compromised, so that the overall solution becomes less robust. So that means that if you try to solve all the equations, you may not be able to get an acceptable solution. So sometimes you may get into non-convergence, divergence of the iterative scheme, like that. So there is a loss of robustness as you move away from the standard K epsilon model towards Reynolds stress models or towards the nonlinear models and all that. So we have to make a balance between the accuracy that we want and the kind of numerical effect that we are willing to spend in getting a solution. If there is a strong reason to believe that a K epsilon model is not correct for a particular flow application, only then we should venture out into the special effects, either for better treatment of the turbulence close to the wall in terms of the K omega type of models, which require more number of grid points, or the Reynolds stress type of models which do not depend on the isotropic nature of the turbulent viscosity as modeled in this, or the nonlinear models which which also do not make this relation linear. So all those special effects should be considered if we anticipate a problem with the K epsilon model. Now there is we have said enough about the flow equations to especially the solution of the Navier-Stokes equations in the case of turbulent flow. But typically we not only have the flow, but we also have the heat transfer, the mass transfer, and the chemical reactions associated with the flow. Now what about those things? Well, how are those equations modified when we consider turbulent flow? The simple answer is that the approach that we have used for the Navier-Stokes equations, for the momentum equations, in terms of Reynolds averaging and then trying to come up with a simplified form of an equation representing the turbulence effect on the overall time average variation of the quantity. Okay, so that approach is extendable readily to the energy equation for non-isothermal flows and to the species conservation equation for the mass transfer and also chemical reactions. So we can come up with a time averaged energy equation which looks very similar, and in such case instead of having a term like ui prime uj prime, we will have a term like uj prime t prime minus uj prime t prime as the equivalent fluctuating energy flux, temperature flux, okay, times Cv will give us the energy flux associated with turbulence, and this is modeled in a very similar way, like this is represented as nu t by something like the turbulent Prandtl number for, okay, we will just put it as Prandtl number here, subscript Prandtl number times dou t by dou xj, dou t bar by dou xj. So this is how we can do this. This is already calculated as part of the solution of the momentum equations, and this value here is roughly of the order of 1. T bar is calculated from the time averaged energy equation. So this is one way of closing this particular equation. So this is the additional term that appears in the time averaged energy equation, and that can be solved like this. Similarly, when we are looking at the species conservation equation, one may come up with uj prime say C prime, where C represents the concentration of the species, and this again can be represented as ut by sigma Schmidt number or something like that, representing the mass transfer, times dou c bar by dou xj. So in that sense when we time average the corresponding conservation equations, we do get into terms which are similar to the turbulence stresses that we have obtained by time averaging the Navier-Stokes equations. We can extend a similar kind of modeling of this turbulent fluxes in terms of the turbulent viscosity and the turbulent Prandtl number, turbulent Schmidt number, and the mean gradients of the temperature and of the concentration gradient like this, and thereby come up with the time averaged scalar transport equations for the energy, and when we come to the wall variation of the temperature and concentration close to the wall, we have to come up with equivalent wall functions. As long as the Prandtl number of the fluid and the Schmidt number of the fluid for the energy flux and the mass flux are around 1, we can make use of very similar kind of variations, wall functions for this. But typically when we consider heat transfer, the Prandtl number of the fluid need not be equal to 1. For many gases it is of the order of 0.7, so it is fairly close to 1, but if you consider some organic liquids, it can be very high, of the order of 100, and if you consider liquid metals, Prandtl number can be very low, of the order of 0.01. So you can have a wide variation of the Prandtl number, and in such cases when Prandtl number deviates significantly from 1, we have to be very careful about the correctness of the wall functions that we use to represent the turbulent fluxes close to the wall. Similarly, when we consider mass transfer, pure mass transfer, we have the Schmidt number, which represents the mass diffusivity to the momentum diffusivity. So that can be very large, and for some organic fluids it can be of the order of 10,000, even 50,000, like that. So again in such a case you have a variation of the concentration profile which is very different from the variation of the velocity profile in turbulent flow, and especially when the Prandtl number is much greater than 1, or when the Schmidt number is much greater than 1, you have the strange case that if you are looking at a velocity profile which is going like this, so this is the velocity and this is the distance from the wall. So this is y here and this is the average velocity. So this is the typical, let us say that this is the turbulent typical turbulent velocity profile. The Prandtl number variation can be like this. That is most of the variation of the temperature. So this is T bar as a function of y. It can be like this if the Prandtl number is much greater than 1, and it can be like this if Prandtl number is much less than 1. And what does it mean here? Your first grid point in the wall functions may be such that your first grid point is here. This is your this is the region in which you have assumed a certain variation of velocity, and you see that for when Prandtl number is much greater than 1, most of the variation in the temperature, mean temperature profile, is already over within this region. So you are imposing an uncalculated turbulence profile on the heat transfer here, and there may be some discrepancy coming from that. And when you are considering this, when you use a wall function which is a standard wall function, that again may be quite wrong here. If you consider a Schmidt number which can be much higher than 1, okay, so Schmidt number much greater than 1, let us say 10,000, then the variation of the concentration profile, it may be like this. That means that typically for these values, even for y plus within y plus of greater than 1 itself, that is within the viscous sublayer itself, see okay, so concentration, mean concentration for y greater than y plus greater than 5, it may become constant. Okay, so the variation of the concentration with y will be within the viscous sublayer. And what is the importance of that? Generally when we talk about viscous sublayer here, we say that k is equal to 0, that is it is purely viscous dominated thing, there is no turbulence within that viscous sublayer. So that is a general thing that we can that we normally ascribe to in this. So that means that in the case of turbulent diffusivity of the species for a Schmidt number which is much greater than 1, in reality there is no there may be some effect of turbulence, but you are imposing no effect of turbulence here. So this is something that we have to consider here, and so as per your wall function which is somewhere here, there is no further variation of concentration profile within this region. So this leads to some discrepancy. One has to be careful about evaluation of the temperature profiles and the concentration profiles for fluids which have a Prandtl number or a Schmidt number much greater than 1. One has to pay special attention to the near wall treatment of these quantities in turbulent flows. So if necessary, one may have to go to models like this, which can take us right up to y equal to 0, in which case we can bring in the natural we can bring in faithfully the effect of molecular viscosity and molecular diffusivity for in the flux of mass flux, species mass flux, and energy flux close to the wall. So that's one thing. Or we have to alter the standard wall functions that we use for the energy and species concentration. So we have to be careful, otherwise we cannot expect to get good agreement between the measured heat transfer coefficient or measured mass transfer coefficient and the computed one, all because not because of the discretization errors and all the computation errors, because we have made wrong assumptions about the influence of turbulence close to the wall for these cases. So where you have wall dominated heat transfer, wall dominated mass transfer, it is important to look carefully at the near wall treatment of the turbulent diffusion of these quantities in case of turbulent flow. In case of laminar flow we do not have any such problem. For turbulent flow we have a problem because we are solving only the approximate form of the equations with assumed model for the turbulent transport of these quantities. So if this is accurate, if this is appropriate, we get good velocity profile, good profiles for the temperature and concentration. If this is not accurate, then we can get wrong values of the profiles and therefore wrong values of the heat transfer and mass transfer coefficients. So this is about turbulence modeling. One can see that in the general case we have to use some sort of Reynolds time averaging of the governing equations, so that we can we do not have to worry about the very fine turbulence fluctuations, temporal fluctuations and spatial fluctuations, but in the process we are coming up with additional unknown quantities like the Reynolds stresses, and these are only approximately modeled in using a vast array of models like this, and therefore the equations that we are solving for turbulent flow are no longer fundamental equations which have to be obeyed. These are only approximate form of equations. So therefore we have to be wary of the errors introduced in the modeling when we are looking at turbulent flows, and there is an array of models which can be from which we can choose that model which is appropriate for our flow. Although the standard K-epsilon model has proved to be a robust model, it may not always give the correct values, and if so we have to anticipate what kind of problems we have, what kind of phenomena we are looking at, flow phenomena we are looking at, and choose to either go for a Reynolds stress model in case we are looking at strong curvature effects or strong buoyancy effects playing a part in this, or if we are looking at strong wall influence, we may have to go for these type of models, or we may have to take careful look at the wall functions that we are using. So one has to judiciously select a turbulence model so that we can solve for the variables of interest, that is velocities, pressure, temperature and concentrations and so on. Finally, when we are looking at chemical reactions, we have to specify the mean rate of reaction, and that is a very contentious issue, and there is a vast array of models when we have a large set of chemical reactions which are happening together, because usually these chemical reaction rates are dependent exponentially on the temperature, and temperature fluctuations may cause a wide range in terms of the chemical reaction rates. So that is an entirely different there is an entirely different set of models developed for that. One has to consider those things before one attempts a serious calculation of turbulent reacting flows. So we have to be informed to make good choices, and I hope this particular discussion has helped in highlighting some of the aspects.